Assalamualaikum, my name is Muhammad Fauzan bin Muhammad Fauzi. My matric number is 2024468264. So, I will present to you about assessment 1 for the assessment 1. So, as you can see for the first question is using the given specifications, sketch the ideal and actual FIR LPF magnitude, respond clearly indicating passband, stopband and transition region, passband, edge frequency, attenuation in the stop band and the expected ripple behavior. So you can see here is for the FP is 1.0 kilohertz. Next one is 0.5 kilohertz, negative 45 dB and 5 kilohertz. So as you can see here, this is the sketch that I have made. As you can see, here is the stop band ripple, the ideal low pass filter, transition with AW, WP, WS, and pi. So this is the pass band ripple. So next is the ideal filter. As you can see, I sketch here negative pi to WL to 0, WC to pi. So if you go a little bit here, you can see the RP is negative 20 log 1 minus 8P. AS equal to negative 20 log 8S. WP is pass band H frequency. WS is stop band H frequency. 8P, for this one is the pass band ripple and the stop band ripple. So next question is design the coefficients of the FIR low pass filter manually to meet the specification given using the Henning window method with the specification in the appendix 1. So as you can see, the formula is LPF equal to 2FC sine WC n minus alpha divided by WC n minus alpha. So FC is FP plus FS divided by 2, or WC equal to 2 pi FC. So next thing is you're going to do the normalization. So FPN is FP divided by FS. So 1 kilohertz divided by 5 kilohertz equal to 0.2 kilohertz. So next is WPN 2 pi FN. We already get the FN. So we just put the answer 0.2 inside the FN. So we get the... So next we get the 2 pi 0 times 0.2 equal to 0.4 pi. So next is... Sorry. So next is Fn. 0.5 kilohertz divided by 5 kilohertz equal to 0.1. So Wn equals 2 pi Fn. So we put the 0.1 into the Fn. So 2 pi times 0.1 equal to 0.2 pi. So for Fsn formula is Fpn times Fn. So we got 0.2 plus 0.1, you got 0.3. So we put in the formula Wsn is 2 pi Fsn. So 2 pi times with 0.3 that we got before. So we got 0.6 pi. So FC is FPN plus FSN divided by 2. So 0.2 plus 0.3 divided by 2. We got 0.25. Again, we put in the formula 2 pi FC. 2 pi times 0.25. We got 0.5 pi. So given AS is negative 45 dB. So the nearest to the AS is Henning is 44 dB. Window function Wn 0.05 minus 0.5 cos 2 pi n divided by n. So FC here is 8.1 divided by n, 8.1 divided by n. So we got 8.1 divided by 0.1, we got 81. So the alpha is n divided by 2, 81 divided by 2 is 15.4. So next is based on the, the next question is based on the design, calculate the causal FIR for an filter order of 32 until 34 that may influence and impact computation cost and long-term energy consumption of device. So the first thing is LPF equal to 2FC sine WC n minus n minus alpha, WC n minus alpha. So we got here n just now, alpha equal to 15.5. So 2 pi FC, 2 pi times 0.25, we got 0.5 pi. I forgot to put the pi. So 2 FC sine WC n minus alpha divided by 2 pi FC n minus alpha. So the first thing, this is the formula. 2fc sine WCN minus alpha divided by 2 pi FC WCN minus alpha equal to 0.05 minus 0.05 cos 2 pi over n. So first thing we're gonna put the n equal to 32 based on the question is the n 32 until 34. So we're gonna do 32, 33 and 34. So for the 32 is sine 0.5 pi 32 minus 0.5 divided by pi 32.15.5 0.5 minus 0.5 cos 2 pi 32 divided by 31. So we got the answer is 0.00014. So for the n33 is same as the before, just we put 33 inside the n. So sine 0.5 pi 33 minus 15.5 divided by pi 33 minus 15.5. So 0.5 minus 0.5 cos 2 pi 33 divided by 31. So next, so we got the answer is 0.000052. So the next thing is 34. We just do the same. You just put the 34 into the n. So sine 0.5 pi 34 minus 15.5 divided by pi 34 15.5 0.05 minus 0.5 cos 2 pi 34 divided by 31. So as you can see here, we got the answer is negative 0.00011. So for the total of the equation that we require is filter order 3235 is, for the first one is 0.0014. Next one is 0.00052 and the last one is negative 0.00011. So that's all from me. Thank you.
Okay, now I will explain the calculation for the selective factor, filter order and the 3B cut frequency. Okay, first I calculate the selectivity factor represented by K. It is obtained by dividing pass band H frequency by the stop band H frequency. From the calculation, the value K is 0.6. Next, I calculate the discrimination factor represented by D using the given passband ripple and stop band attenuation value. The calculated value is 0.2237. After obtaining both value, I determine the filter order represented by N. By substitute the value into the formula, I obtain N equal 2.93 since the filter order must be whole number is rounded up to 3. Okay, next finally I calculate the 3 dB cut frequency or omega C. Based on the calculation, the value of omega C is 0.3365. This value will be used in the next step to determine the pole of Butterworth filter. Okay, next, determine the system function based on calculate left hand side poles. In this section, I calculate the left hand side pole of the Butterworth filter. Since the filter order is a 3 pole, which PO1, PO2, P1 and PO2. So using the cut-off frequency of 0.3365, each pole was calculated using the Butterworth pole equation. The calculated poles PO0 is 0.1683 plus J 0.2914 and P1 negative 0.3365 and P2 is, this one is P2 equals 0.1683 plus J 0.2914. These poles are important because they determine the stability and frequency response of the filter. After calculation the poles, I construct the transfer function HS. The transfer function is formed by combining all the poles in the denominator and using the gain in the numerator. The equation represents the mathematical model of the design Butterworth low pass filter. present the frequency response of the Butterworth low pass filter. This first graph show the magnitude response. We can see that the magnitude remain close or 0 dB at low frequency. That means that low frequency signal pass through the filter with very little attenuation. As the frequency increase beyond the cutoff frequency, the magnitude decrease gradually. This show that the filter efficiently attenuate high frequency signal while allowing low frequency signal to pass. The second graph show the phase response. The phase response decrease as the frequency. The behavior is normal for the Butterworth filter and indicate that the filter introduce phase shift at higher frequency. Okay, for the last graph is another view of the magnitude response. A smooth roll of the without ripple in the passband. The smooth response is one of the main character of a Butterworth filter, which is known as a maximal flat response. This slide, the first graph show the phase response in radian. The graph indicate that the phase become more negative as the frequency increase. The gradual change show the normal phase characteristic of the design Butterworth filter. The second graph is the pole zero plot. In this plot, the crosses represent the pole while the circle represent the zero. We can observe that all the poles are located inside the unit circle. This indicates that the digital filter is stable. The pole location also produce the smooth frequency response that is expected from Butterworth low pass filter. Okay, so in conclusion, the Butterworth low pass filter was successfully designed based on the given specification. The selectivity factor, discrimination factor, filter order, cut off the frequency pole, and transfer function were calculated successfully. The frequency response show that low frequency signal are passed with a minimal attenuation, while high frequency signal are efficiently reduced. Finally, the pole zero plot confirm that the design filter is stable and perform according to the required specification. Right, thank you.